This video is a bit off topic compared to the previous videos, all of them easily accessible by the playlist provided. It's about a discovery I made when playing around with evolutionary strategies many years ago. Back then, I had the idea to apply evolution to Turing machines. A Turing machine is a virtual computer model with a very simple architecture. It was invented by Alan Turing. A Turing machine consists of 4 components: a tape, consisting of discrete cells in a row, a head, which reads information from the cells and can write information to the cells, a state register that describes the current state of the Turing machine, and a table, which stores the instructions, that is basically the computer program. I adapted this model for my purposes by modifying the tape to be 2-dimensional, with the cells holding only one bit of information, that is 0 or 1. Of course, also the head now had to move in 2 dimensions in order to work on the tape. In the theoretical model, the tape is infinite, which of course had to be limited in my actual implementation. In fact, the tape was basically the screen of my computer. So these Turing machines were living happily and evolving my computer, and during that process, by chance, I found a very simple Turing machine which revealed an interesting behavior. The Turing machine I found had just 1 register and 2 table entries. It read, if the cell where the head is currently located contains a 0, then change this 0 to a 1 and move the head to the next diagonally upper right cell. If, in contrary, the cell where the head is currently located contains a 1, then change this 1 back to 0 and move the head 1 cell to the left. Mind that all cells at the beginning contain 0. On the screen, a 0 is represented as a black pixel, a 1 as a white pixel. We are starting with the cell in the bottom row mid-screen and call this the starting cell. When during the course of the execution the head reaches any edge of the screen, we will put it again back onto the starting cell. Now, this doesn't sound too exciting, I guess, and if you look at the pattern this Turing machine is generating, it in fact looks rather boring in the beginning. It's drawing wide diagonal lines. Only in the area right above the starting cell some more interesting pattern appears. But now let's look at this in high resolution and high speed. Isn't that amazing? Such a complex pattern emerging from such a simple Turing machine. As a next modification, I introduced shades of gray instead of directly switching from black to white. So a pixel first visited would be colored in a very dark gray, that is almost black, and the gray shade would get brighter with every visit. Pixels visited many times, like for example the starting cell, would soon become completely white, whilst pixels visited only once would stay basically black, for example the first diagonal lines. In order to visualize how the Turing machine is working, we can indicate the path the head is taking during one pass, that is, from the starting cell until an edge of the screen is reached. At first, you just see the movement of the head, but after some time, the pixels of the emerging pattern become brighter as cells are visited more often. There is another interesting aspect. This Turing machine does not only generate an interesting pattern, but this pattern is also self-sustaining. Let's put a horizontal wall in the middle of the screen. When the head of the Turing machine reaches the wall, the pass ends just as for the edge of the screen, and the head is sent back to the starting position. But a little hole in the middle of the wall allows the head to pass through. Let's run the Turing machine and see what will happen. After some time, we see the same pattern appear a second time emerging from the hole. We can extend on this and use a wall with two holes. The two upper patterns merge without destroying the overall structure. Using two different colors, it is easier to see how patterns interact and merge. For this purpose, we are using two of these Turing machines at the same time, generating their pattern in different colors. Instead of having two patterns side by side, we can force them to cross. It is not only interesting to watch the crossing area, but mind how the disturbance caused by the crossing is overcome and the original pattern is recovered. Another example now with more colors. 4 of these Turing machines running concurrently. Isn't that cool? Let's have a last change for this pattern. Before, we used shades of gray to visualize how often a pixel had been visited. Now we are extending this to colors. For the experts among you, we are simply using the 24-bit RGB color value, starting from 0 and incrementing it every time we are visiting a pixel. Enjoy! During the course of the presented videos, we have introduced a quite simple model for artificial life. Despite its simplicity, we discovered astonishing properties. Of course, there would be a number of natural extensions to our model. Up to now, our creatures were represented by a single pixel. What if we'd allowed them to grow and develop spatial structures? It could look like this development, which I played with some years ago. In this case, I have the structure developed in an evolutionary fashion, favoring structures which would maximize the number of yellow pixels in a given area. That's why we see it grow. Matching this idea to the model we developed in our videos, a potential growth of the organisms should not be guided by such a given goal, but should instead be simply in favor of their survival and hence emerging naturally. Again, we would suspect their appearance to be dependent on the environment. There is a second natural extension to our model. Up to now, our creatures are without any senses. They move about, but neither can they sense food in order to move in its direction, nor can they sense other organisms in order to avoid contact. Again, the challenge would be to have a model which would mimic a natural development of such senses. Of course, some sense organs have to be added to our model, but the way in which organisms would react on sense input could be completely up to natural selection for survival. Some time ago, I programmed an algorithm to play tic-tac-toe. It started out completely blank, not even knowing the rules. Breaking rules, of course, meant to lose the game. The program learned by playing against another algorithm which would select valid moves based purely on randomness. After 70,000 games, my program not only knew the rules, but played perfectly. A similar development regarding the reaction on sense input could be used within our evolutionary model. And again, it should not be guided by a given goal, like playing tic-tac-toe, but should simply be in favor of survival. I hope you found the topic inspirational and the videos helpful to explore a little bit how artificial digital life might loom in the future.